Okay, let's consider a 6 kilogram mass resting on a frictionless surface. So it can be moved about. The forces that are acting on the mass will be the gravitational force acting downwards, and that is 60 newtons, and of course the push of the table acting upwards, that is the normal reaction force, also 60 newtons. So in this case, there is no resultant force or net force on the 6 kilogram mass, so it will remain stationary. Now if we wanted to accelerate this mass in any particular direction, we must apply a net force. One way we could do this is to attach a string to it and pull it to the right. Since the surface is frictionless, the mass will have a resultant force or a net force to the right, and therefore accelerate to the right. Another way we can apply a net force on the mass is if we attach a string to a hanging mass. In this case, if we hang a 4 kilogram mass by means of a string, then the 4 kilogram mass will have a gravitational force of 40 Newton acting on it, but the mass is interconnected by a string to the 6 kilogram, and therefore we have a system of interconnected bodies. Both these bodies, the total mass of 10 kilograms, is being pulled by a 40 Newton force. We can apply Newton's second law, acceleration equals F net divided by mass, to a system of interconnected bodies, much like we did before. An external force of 40 newtons, that's the net external force, is acting to accelerate a combined mass of 10 kilograms. Therefore, the acceleration of the bodies of the system will be the F net, 40 newtons, divided by the combined mass of 10 kilograms, and that will give us 4 meters per second squared. Since both of these bodies are interconnected and moving together, then both the 6 and the 4 kilogram mass have exactly the same acceleration. That is 4 meters per second squared. Now the string that interconnects the two masses is under tension. We need to find its tension. So the tension force acts on the 4 kilogram mass upwards, but the same tension force is what is pulling the 6 kilogram mass to the right. So this rope being under tension is pulling the 4 kilogram mass upwards, but it's also pulling the 6 kilogram mass to the right. The values of the tension here must be the same because it is the same string. In order to find the tension, we can concentrate on either of the two masses. We shall do both. Looking at the 4 kilogram mass and applying Newton's second law to this, the F net equals m times a, and so the net force will be 40 minus the unknown tension T. So 40 minus T, being the F net, is equal to the mass, which it is accelerating, of 4 kilograms, times the acceleration, which we have already found by considering the system as a whole, as 4 meters per second squared. Substituting into the equation gives us that the tension force is equal to 24 newtons. A similar analysis can be done by looking at the 6 kilogram mass. The resultant force, or the net force, being the tension, and so if we apply this formula, Newton's second law, the net force, being the tension, is equal to the mass times the acceleration, the mass being 6 kilograms, the acceleration 4 meters per second squared, therefore the tension in the string is 24 newtons. It is no surprise that the tension found by considering this mass and the tension found by considering this mass is 24 newtons in both cases, because the tension is the same as if we have one string over a pulley that is free to rotate. Now, how would the situation change if there was a frictional force? Well, if this was not a frictionless surface, there would be a frictional force acting opposite to its direction of motion. In fact, if the frictional force was 20 newtons, then we can look at the whole thing as a system again. And we can say that the acceleration can be found by looking at the net forces divided by the total mass. The net forces externally, though, are 40 newtons acting to pull the system this way, and the opposite side of the string acts 20 newtons to pull it in the opposite direction. Therefore, the resultant force, or the net force, is 40 minus 20. So the net force now becomes 40 minus 20, accelerating a combined mass of 10 kilograms. Thereby, the acceleration is now 2 meters per second squared. This will obviously change the size of the tension force. Looking at the free body force diagram for the 4 kilogram mass, we have the net force being 40 minus t, net force being 40 minus t, will cause the mass of 4 kilograms to accelerate this time by 2 meters per second squared. And doing the mathematics means that the tension force is now 32 newtons. As before, we can look at a free body force diagram for the 6 kilogram mass. In this case, the net force will be the tension acting to the right minus 20. Remember, the normal and the gravitational forces balance out. And so T minus 20 is the net force, T minus 20. And that net force is acting on the 6 kilogram mass. And so it's equal to m, which is 6, times the acceleration of the system, or of the 6 kilogram mass 2, which we found to be 2 meters per second squared, thereby also leaving a tension force on the rope of 32 newtons. We have considered the simplest case of an interconnected system of bodies involving one hanging mass and one body. One can easily visualize how this system can be extended to involve more hanging masses and more masses being pulled along the